I will show now that Rn cannot allow for too many linearly independent vectors. Yeah, so suppose we have linear independent vectors v1 till vm, so we have m linearly independent vectors in Rn. Then we make a matrix A with these vectors as columns. So A equals the matrix v1, v2, and the final column is vm. Then we look at the linear relations that may occur or that we may have between the v1 and vm. So we write down the equation and try to solve it for c. c1 v1 plus c2 v2 plus finally cm vm equals the zero vector is equivalent with the statement that the vector c consisting of the scalar c1 till cm equals the zero vector. So which means that the vector c is in the kernel of A. We have as a given fact is that v1 to vm, they are linearly independent. So if we read the former theorem well, then this means that only the trivial relation resides, and then we know that the kernel is equal to the zero vector. So we have the smallest possible kernel. Moreover, we know that the kernel of a matrix equals a zero vector if and only if A is of full rank. So this means that the rank of A, the number of pivots in the reduced row echelon form, equals m. Also, we know that the number of pivots for a given matrix is of course smaller or equal than the minimum of the number of rows and the number of columns. So we have that the rank, which equals m, is smaller or equal than n. So starting with a number of vectors v1 to vm, which are linearly independent in Rn, leads us to conclude that the number of vectors should be smaller than n, which means that in the Rn there are at most n vectors that are linearly independent.